hello again, and welcome to the presentation about student space activities in Wuerzburg, Germany. I will present the recent advances we've made so far with the UBE series of satellites, and then I will hand over for the future things to Alexander. In Wuerzburg, we've had a long-term roadmap established already in 2005 with the University of Wuerzburg Experimental Satellite number 1. And this roadmap aims at formation flying satellites, and we wanted to do it in relatively small steps, and this has been very successful so far. And just actually 2 years ago, or 1.5 years ago, about UBE 3 was launched to demonstrate attitude control, and I will go into details a little bit on that in a second. The next steps will be orbit control, so position control, relative navigation, and in parallel we're preparing a formation flying mission to incorporate all of the knowledge we've gathered so far in the NetSat mission. UBE 3 was launched in November 2013, and you can see the final integration of the satellite here and testings, as well as the launch sequence. We've operated it since then. It's still operational, and we're still operating it for the future because we found that we can do a lot of things that we haven't thought about before launch. And we've done 3 extensive software updates, just one last week actually, that give us even more capabilities and add features to the satellite. And this will be one of the biggest lessons learned, that this is necessary on all levels of the satellite for a student satellite, because there are many things you don't think about at the moment you build it, but you can fix it or you can even improve it during the mission. The satellite was built in a new manner, and the UNISEC Europe bus system definition is linked to this, and UBE was built from this bus basically, and you can see the different components here. It's a modular system that is basically just plug and play almost. You plug in the subsystems, and if we develop new subsystems, we just add it to the satellite system, and we will talk about this when it comes to UBE 4. The attitude control system has been demonstrated in orbit already. You can see some in-orbit data here. 2 experiments, actually 1 experiment where we set the spin rate of the satellite from in a step control basically from -10 degrees per second to 10 degrees per second in one axis, and the satellite performed that within 18 minutes, this transition, and it was kept pretty precise. There's some deviations here, and those are also due to a lesson learned we've had with this satellite, which is due to a magnetic dipole moment of the satellite that is complicating attitude control. And this is one of the things we'll be working on in the future, because we think that it's possible to control the satellite precisely with adequate and adaptive control mechanisms, but this has not been implemented because the disturbance was not known before launch. Here you can see a detumbling algorithm experiment, and it's actually pretty interesting because this is a very efficient detumbling from almost 80 degrees per second. So I don't know of any other satellite, a CubeSat, that has done that from such spin rates. We detumbled the satellite, just pure magnetic control, within 40 minutes. It's not written here, but it's 40 minutes from more than 80 degrees per second. And we can even improve that, because we know that at that time there were some software issues with the control system that are now not there anymore. So you can see that improving a satellite, even when it's already in orbit, is actually a big thing, and is a big opportunity for students to keep on working on a satellite even though you don't have it at your hand anymore. We've seen another very interesting and very disturbing issue with the satellite, which is a huge frequency interference. And also, again, due to a software update, we were able to characterize this frequency interference. And you can see the radio amateur band, UHF band, split into 200 kilohertz sections here, and the noise recorded by the satellite being plotted over the Earth. And you can see these red spots. So there's a red spot over East Asia, China, Japan, I don't know. And there are at some frequencies, huge red spots over Europe. And those two frequencies were our initial frequencies with the satellite, and we had huge problems contacting the satellite. Not because we had no problems from the satellite for the downlink. So we could receive all packets from the satellite from the very start, and it was a very strong downlink from the satellite. But the satellite had problems hearing us because this huge interference you can see here. And after measuring this and after some negotiations with the radio amateurs in Germany, we were able to move to a different frequency, which is much better in the uplink. So frequency allocation and again frequency change in orbit might be a very important lesson to learn from our experience. Let me conclude. So we built a modular satellite and reduced the complexity of the system by a lot. Professor Schilling already mentioned this. It took us about 1 hour to integrate the complete flight model of the satellite. We've been testing, and I can't emphasize this enough. We've been testing during all stages of the project, and the students that built these subsystems, they tested at their desk, and whatever they built, they tested. And so the responsibility for the student is high to show that actually their subsystems they're developing actually works. We've been implementing a lot of redundancy and latch-up recovery systems, and just last year we had a severe latch-up condition in one of the radios which could only be resolved by a having a redundant radio and algorithms running on the main computer to resolve these latch-up conditions. So this was also a very interesting thing to see. I mean, we can't avoid latch-ups because we're not using space or radiation-hardened components, but we can, by implementing in a smart design, we can work around and recover them. As I said, software updates played a very important role for us, and the radio community, the radio amateur community, and ground station networks can be even better integrated into our systems, and we would like to continue with that, especially in the ground station network, also for uplink. And I would be very happy if people also interested in that would approach me, because we're looking for partners in this respect. We've learned that you have to be very careful about magnetic materials in a satellite. I mean, most of you probably know that already, but in the CubeSat domain, it's a common mistake apparently. So we're not the only ones that made this mistake, but I can tell you it's not a good thing to use any magnetic material. We've most probably found the cause for this magnetic dipole we have in the satellite, and for sure UV4 will not have it anymore, but other student projects can learn from that a lot. However, with software updates we can work around it, and I think we can do the attitude control much better when we know this dipole already. Frequency interference was a huge thing, and to characterize it, and maybe last but not least, we think that the PC104 standard or quasi-standard is really not good for those things such as CubeSats, and the new CubeSat bus standard put forward by UNISEC Europe, I think it will help a lot to better cooperate in the student CubeSat community. All right, we'll hand over to Alex now for the future missions, basically.
Thank you. Okay, you've heard so far from Philip about the past developments and past missions that have happened so far at the University of Wuerzburg. I will tell you now about the near future missions and project plans, which is on the one hand UV4, the next University of Wuerzburg experimental satellite, with a goal of implementing electric propulsion on a 1U CubeSat. Therefore, we have several partners where we're looking into their technologies for propulsion for a 1U CubeSat. This is a very challenging task because a 1U CubeSat, as you all know, doesn't have much volume or mass to give away for a propulsion system. So So therefore, we are looking to, we're hoping to integrate it here in the CubeSat rails, which would add some functionality to this so far only structural component of the satellite. There we have two partners. On the one hand, there is the Technical University of Dresden, which is developing small deep thrusters, and the German University of the Federal Armed Forces, who are developing vacuum arc thrusters. They have both approximately a size of 2 to 3 cubic centimeters, which would make them suitable for a 1U CubeSat. This would open the possibility for attitude and orbit control with a 1U CubeSat for a single satellite only. The launch, well, will be as soon as possible. As soon as we have the propulsion system, the electric propulsion system for the satellite, we can gain from the heritage that we have from the UWE-3 subsystems, the knowledge that the lessons learned that we have from UWE-3 mission, and reuse some of the parts from this mission. In parallel, we have a formation flying CubeSat mission, NetSat. Philip mentioned it earlier already. There we have several challenges to face as well. There is inter-satellite communication in between the satellites. The goal is here to have 4 1U CubeSats flying in an autonomous 3D formation. We have distributed sensor systems in between the 4 single satellites for relative navigation, for example. And we need some advanced autonomous and adaptive control strategies for the not only for the single satellites, but also for the formation control of the whole CubeSat formation. In this respect, we're implementing a new simulation framework with an extended simulator for formation flying satellites. This has to be, on the one hand, multi-rate, because it has to implement the different systems, 4 satellites simulated at the same time with a hybrid system, meaning we have on the one hand side continuously changing parameters, and on the other side we have some event-based things happening, like maneuvers from the electric propulsion system or user inputs. Additionally, this simulator shall give the possibility for hardware-in-the-loop tests on different levels. As Philip mentioned before, with UWE-3, we've seen that the testing for the students on different levels helps a lot already in the development process. Therefore, we want to have this hardware-in-the-loop tests on component, subsystem, and system level afterwards. The goal is to have it incorporating as much as possible from the formation flying mission, so also having communication and subsystem simulation with all the sensors. Additionally, for hardware testing, we have a study going on right now for a formation flight test center to have a test facility regarding, on the one hand, the inter-satellite communication and hardware-in-the-loop tests for control systems. But this is not all, so there are also the other tests going on, other equipment that we need for vacuum chambers to test the satellites properly. Additionally, we want to do relative navigation tests. That's what you can see already here on the left figure. We have 2 KUKA robots with PMD camera tests for rendezvous and docking maneuvers. That's it for our presentation. Thank you for your attention. If you have any questions, happy to answer.
To formation flight, or do you also invite outside to join your programs?
At the moment we're having, well, UWE-3 is in orbit, UWE-4 will be launched as soon as possible, and this NetSat mission will be 4 single satellites. But I think the possibility would also be there to open this for bigger formations. Other questions?
Thank you very much. Any questions? Okay, thank you very much. Next, sorry, I forget to announce that Mongolia and Nigeria, the presentation are cancelled. And the